So one concept we need to cover before jumping into rotational motion is called the center of mass. The center of mass is where an object can be balanced. So we often call this center of gravity as well. Now, technically, center of mass and center of gravity are not the same thing exactly, but that really doesn't come into play when we're talking about objects, small objects here on Earth. The difference really comes into play if you're talking about a skyscraper, that type of thing, which we're not going to be doing that. Center of mass. So for example, let's say I had a meter stick. Or a thin rod, some sort of bar, some sort of rectangle. If I put my finger or I hold the object exactly in the middle, it will stay balanced. Or at least in theory. It's really hard to balance it. Balanced meaning it's not going to fall one way or the other. That's what we mean by an object can be balanced. It is possible if I take the meter stick and held on to it at the end, it would swing down and end up coming to rest directly below my fingers. So in this case, if it's at rest below my fingers, it is technically balanced here as well. It's in a state of equilibrium. It's not going to keep rotating or start rotating. What this boils down to is a concept we call torque, or in engineering they call it moment. I don't know why we use different words, but torque or moment is the tendency for rotation to occur. So coming back to the example where I'm trying to balance this meter stick on my finger, I know if I don't have it exactly right, it ends up falling to one side or the other. The torque is the twist, that rotation that ends up occurring. So what we're saying when we're talking about center of mass is if we have our finger exactly at where we call the center of mass, the net torque is 0. So what we mean by it can be balanced, we say the net torque is 0. The net torque or twist is 0. Now, in the case of a meter stick, this half of the meter stick would totally have the same mass as this half of the meter stick. Both halves would have the same mass. In terms of anything that has some symmetry and is made of any one given material, the center of mass is in the geometric center. So for example, a disc, cylinder, its center of mass will be in the exact center of the disc. Now, what we talk about center of mass for is to talk about the force of gravity. We know the force of gravity depends upon mass and g. Again, we're still fine assuming constant g because our problems are still taking place on the Earth. G is more or less constant. But if we think about an object, the meter stick or the disc, every single piece of this meter stick has mass. Therefore, every little tiny piece of the meter stick is feeling or experiencing its own force of gravity. Pieces on this other side are also feeling the pull of gravity, which we don't want to break an object up into a whole bunch of little teeny tiny pieces of mass if we don't have to. Every single piece in the disk would be feeling the pull of gravity. The center of mass is a way to talk about any one given object and how the force of gravity acts on it. So coming back to the meter stick, the center of mass is in the geometric center of the meter stick. We can treat the center of mass as the point at which the force of gravity is acting on an object. Now, realistically, of course, it's not acting only there, but mathematically, we can treat it as if it were acting only there. If the meter stick was hanging vertically, we would draw the force of gravity still acting on that exact center. For our disk, we would treat the disk as if the force of gravity were acting exactly at the center. Now, to be balanced, well, when I have my meter stick and I hold it on the edge, well, the force of gravity is acting over here, and I'm not supporting the meter stick at that location, and so that causes what we call a torque or a twist. It causes the meter stick as a whole to rotate because we're not supporting the meter stick at the location gravity is acting. We're not counteracting gravity properly. That would be true for the disk as well. If I held the disk on the side, the force of gravity would cause this disk to twist or turn, to rotate. So this force of gravity, if it's acting some distance away from where the object is held in place, we call this the rotation axis. If there's some distance away and that force, then the meter stick can turn and start to rotate. So center of mass is a way to talk about how the force of gravity acts on an object, and it just simplifies calculations and accounting for gravity in general. Okay, I have a or a conceptual question to ask you. Just let me go get it. And let's see if this will paste. Of course not. All right, here's the question. What do you think? So the correct answer here is B. Now, it's really common to think of center of mass as the two halves having the same mass. But again, that's not necessarily the case. It can be the case for an object that is made entirely of the same material. But a hammer, of course, is not. We have the handle, and then we have the head of the hammer. Do my best. There we go. So what this problem is telling us is if we hold the hammer right in here, then it can stay balanced. That means the center of mass has to be directly above our finger in order for it to be balanced. And again, center of mass, the location of the center of mass means we are completely balancing the force of gravity. as if it were acting only at that point. Yet, if we actually cut this apart so that we had just the handle and then just the head would be heavier. That's the purpose of the head, is to be heavier so that when we swing the hammer and hit it against a nail, the nail can actually move into the board. Going back to this concept of gravity, the handle can be thought of just in and of itself as a uniform piece of wood. Some handles are probably thicker at the end, but we'll ignore that part for a minute. The force of gravity on just the handle would be acting approximately in the center of the handle. The center of mass of the head is going to be up here closer to the middle of the head. If I come back to my original picture, this distance to where the force of gravity acting on the handle, I'll call that R1, versus I can hardly see the distance from the center of mass to where the mg of the head would be. So this is for the handle, this is for the head. Center of mass is where we can balance an object, where we can treat the object as if the force of gravity were acting only there. As we talk about torque in the next section, torque depends both on the force and how far that force is applied from the rotation axis. When we have a larger distance from the rotation axis in this case is the center of mass, because that's where I'm balancing it. So that's where it will rotate about if I don't maintain the balance perfectly. A bigger R, bigger distance from rotation axis, means a lower or smaller value of a force. A smaller R means a bigger force. This head needs to have, or does have, more mass because the center of mass is located closer to it. Now, in terms of calculating center of mass, technically it is a Calc 2 problem, which means we're not going to do much in terms of the full-on integration. But technically, to calculate for any given object, we need to break the object up into little infinitesimally small pieces of mass. We call those DMs, infinitesimally small pieces of mass. And we need to add, so integrate, their location from the rotation axis. And then we have to divide by total mass to make this an overall distance. Technically, this needs to be done along the x-axis. So we would integrate the x distance, the horizontal distance of each piece of mass, but we would also need to write dm in terms of a dx. This is more involved than what we're going to do because we don't have Calc 2 as a prerequisite for the course. For those of you that get to take statics, you will do this in statics to some extent. And so this integration would need to be done for all three directions, x direction, y direction, and z direction, to pinpoint exactly where the center of mass is. Now we can approximate this if we only have a couple pieces to talk about. we can literally just do the summation of a piece of mass times its distance from some sort of origin. And that's true for all directions. So mi(xi) means we're summing over I number of pieces. These equations are in the test notes. So let me show you what I mean by something like this. Let's say we have something relatively simple, because it needs to be simple in order to use that simplified version. Let's say we have some sort of L-shaped object. The dimensions, let's say this is maybe 15 centimeters by 15 centimeters. And then this side is 5. And this side is 5. And just in terms of x, y, where would the center of mass be located? So this object has a total mass m. Let's give you a value. Let's make it 4 kilograms, which is a rather large mass probably for this object. Now it turns out any object, so going back to the meter stick, any object that has a both physical symmetry and then is made of a uniform material, the center of mass will be in its geometric center. So a meter stick, the center of mass, I'm going to just abbreviate it, cm, would be in its geometric center. A disc, same thing, center of mass will be in its geometric center. A hoop or a ring, just like a wedding ring, its center of mass would be in its geometric center. So if we come back to this picture, this L-shaped object, we can treat this as 2 rectangles. The center of mass of this bottom rectangle, I'll call it rectangle 1, would be in its center. The center of mass of rectangle 2 would be in its center. We can use these 2 equations above to find the x location of the center of mass and the y location of the center of mass. If we first define a coordinate system, we need to know where we're measuring x and y from. It turns out we can put that wherever we want, and then our answers for x and y will be in terms of that coordinate system we chose. For simplicity's sake, I'm going to say the origin of our coordinate system is the bottom left-hand corner of this L-shaped object. So here's our x-axis horizontally along the bottom of the L, y-axis vertically along the left edge of the L. With this coordinate system defined, we can write the locations of these individual center of masses. So for example, this bottom rectangle has a location. Half of the 15 centimeters would be 7.5 centimeters in the x direction, and then half of the 5 would be 2.5 in the y direction. This is what we mean by x1 and y1. When we come back up to our equations, we have x sub I and y sub I. We mean x1, y1. And then we'll add up the m2, x2 to that. So the coordinate of this second piece is going to be 2.5 centimeters. And then, let's see, this whole length is going to be 10. Half of that is 5. So 5 and 5, this y position, y2 is 10 centimeters, x2 is 10 centimeters. Now, in terms of M1 and M2, we need to figure out how much mass each of those two rectangles would have. If I think of this whole setup as a bunch of 5 by 5 squares, this rectangle 2 has 2 squares. Rectangle 1 would have 3 squares. The whole thing is 5 squares. So we can say that M1 has 3 of the 5 squares. So we would take 3 of the 5 times the total mass. So 3/5 of the 4 kilograms is M1. Similarly, M2 would have 2/5 of the total mass. 2/5 of the 4 kilograms. So we're essentially saying this object is made of 2 rectangles, and we can find the center of mass by adding M1, X1, M2, X2. So mass times X position for the 2 rectangles divided by this capital M in the equation just means total mass. So M1 plus M2 in the denominator. If we plug that in, M1, this is 12/5 kilograms. So 12/5 kilograms. X1 is the X position. I'm going to leave it in centimeters. So that's my M1, X1. My M2, let's see, that's 8/5 times X2, 2.5 centimeters. And then I need to divide by the total mass, which is the 4 kilograms. So the kilograms units are going to cancel. Our units for this X location of center of mass will be in centimeters because I'm leaving X1 and X2 in centimeters. I'm getting 5.5 centimeters. What that means, if I come back to my picture and measure along the x-axis 5.5 centimeters, the center of mass has to lie somewhere along this line that represents X center of mass. Now that doesn't tell us exactly where it is. We can find exactly where it is by solving this equation again, but for y. So we're going to take m1 y1 plus m2 y2, divide by the total mass, and this will give us our y location of the center of mass. So y1 is 2.5, m2 is 8/5, y2 is 10. And by the way, when we add the 12/5 and 8/5, we get 20/5, so the 4, total 4 kilograms. We get the same thing. 5.5 centimeters, which hopefully is not surprising because I made it symmetric. What this means is if we go on the y-axis up 5.5 centimeters and draw a line, y center of mass has to be located there. This point right here that they just intersect at, that is the center of mass. The center of mass is located right there. It's not even physically on the object, which is fine. That's not necessary. The center of mass does not need to physically be located on this object. What this means is the force of gravity, if we were going to talk about rotational motion of this particular object, the force of gravity we could treat as if it were acting exactly at that point. So the purpose of the center of mass is to simplify the way in which we look at the force of gravity. It helps to simplify the calculations. As far as questions go for you, the only type of center of mass you need to calculate is along these lines. Some sort of object that we can just break down and treat as 2, at most 3, maybe 4, just small objects to find the center of mass. And then you will not need to integrate. The other option is going to be some sort of symmetric object, like the meter stick or a disc, where we can just say the center of mass is physically located in the geometric center. So one more example really fast. Let's say we had 4 masses. Let's say this one's 1 kilogram, 2 kilograms, 3 kilograms, 4 kilograms. And they're all a distance of 1 centimeter apart. This is another example of where you could find the center of mass. So where is the center of mass? So here they're just small little balls, so we can treat them, for example, this 4 kilogram ball, if we wanted to make this the origin, so my x-axis and y-axis intersected at the 4 kilogram ball, we would say its coordinate was 0, 0. I'm not sure why I put another comma. The 3 kilogram would be 1 centimeter, 0 centimeters. The 2 kilogram would be 1 centimeter in the x direction, 1 centimeter in the y direction. This 1 kilogram would be 0 for x and 1 centimeter for y. Those are my x's and y's. So again, my equation just becomes a little longer because I need to account for each object. But this really doesn't make it all that much harder. I hope you feel that way. Just a few extra pieces to plug in. So I'm going to say M1 is my 1 kilogram block. Since I labeled them 1, 2, 3, 4, let's just make M1 X1 for the 1 kilogram, M2 for 2 kilograms, and so forth. So mass 1 is 1 kilogram. Its x position is 0, which means I don't technically need to write that term. Mass 2 is 2 kilograms. its X location is 1 centimeter. M3 is 3 kilograms, its X position is 1 centimeter. M4 is 4 kilograms, and its X position is 0. And then we have to divide by all of these masses added together, regardless of their X position. So let's see, 2 plus 3, we get 5 in the numerator, 4, 5, 6, 7, 8, 9, 10 in the denominator. So I get 1/2. The kilograms will cancel, the centimeters will be our units. So to draw this in the picture, 1/2 centimeter in the X direction would be right in the middle. Okay. That doesn't pinpoint the center of mass. We have to also find the Y location of the center of mass. So M1Y1 plus M2Y2 plus M3Y3 plus M4Y4 So M1 again being my 1 kilogram, its Y location is 1 centimeter. The 2 kilogram mass, its Y location is also 1 centimeter. The 3 kilogram mass, its Y location is 0. The 4 kilogram mass, its Y location is 0. And I'm going to go ahead and they add up to be 10, so I'll just leave it at that. So let's see, we get 3 tenths centimeters. So coming up on my picture, 3 tenths, that's going to be approximately 3.33, about 1/3 of the way up. This line is how far the Y location of center of mass is. Oops. So this way. This point where they intersect is the location of the center of mass. Meaning we could treat the force of gravity as if it were acting only there. Now, interestingly, the X center of mass is exactly in the middle, but the Y center of mass is closer to these two at the bottom. Now, the reason X center of mass is exactly in the middle is because on the left side we have 5 kilograms. On the right side we have 5 kilograms. But when we look at top, that's 3 versus bottom, that's 7. That's why the center of mass is closer to those two bottom masses. It's just because there's more mass down there. You will see problems on the homework that have you find center of mass for something like this. But as we continue through the chapter, you will also see problems that have you treat that center of mass as if it were the rotation axis, meaning the whole system is going to rotate. So that center of mass, you could think, is holding everything in place, and then these 4 masses are connected together, and they could technically rotate one way or the other around that axis. So the axis itself, if this is our rotation axis, imagine a a pole of some sort, not really a thick pole, but some sort of wire that's coming in and out of the page that these are now potentially able to rotate around. So I don't draw 3-dimensionally very well. So coming in and out of the page, and then these guys can rotate around it. So center of mass allows us to easily or relatively easily treat the force of gravity as if it were acting at only one single spot. And that ends up simplifying being able to account for the force of gravity in our problems.